Okay, so now we have the last part of this session, a very nice panel of experts from on quantum error correction from academia and industry. So first up, I'd just like everyone to introduce themselves and tell us kind of their background and what they work on. So maybe we start at the end of the line with Christophe. I think it's just going to be on.
Okay, perfect. So yeah, hi, I'm Christophe Vuillot. Right now I'm working at Alice and Bob, leading the QEC quantum error correction team. And actually, I was just before that I was at Inria in Nancy.
Hi everyone, my name is Joan Camps. I'm from Riverlane in the UK. Riverlane, we're building the quantum error correction stack, which is the classical compute that you need to do error correction in real time. And at Riverlane, I lead the decode team, which is the team that designs decoders and also puts decoders on FPGAs to run efficiently in real time. Yeah, that's me.
Hi, I'm Paul Hilaire, and I took the opposite path of Christophe. So I used to work in Quandela, and now I'm a junior professor at Télécom, working on quantum error correction and the architectural part where it interacts with the hardware.
Hi, my name is Boris, Bourdoncle. I work at Quandela. So I used to work with Paul. And I'm the team lead for scalable architecture research. So it means working on the computing architecture for the kind of devices that we have now, small noisy processors, and planning all the way to large-scale quantum computing architecture. So in particular, fault-tolerant quantum computing research.
Great, thanks. And so I think from my perspective as a researcher in this field, there's like been an explosion of papers and results that have been coming out in the last like couple of years as it's got more kind of important, more people working on it. So I'd be curious to hear from you all, like what was the result in the recent years that you really found kind of exciting or surprising? So maybe we start this way around this time.
So surprising, right? You said.
Yeah, or one that you really kind of surprised you and you found very interesting, and it can also be your own result. That's fine. Like no judgment about that.
So during the past year, I think that there is something that I found a trend that I found interesting, which is the return of concatenated codes. With different results related to that, and which is also what I find interesting. So code concatenation was kind of like the early days of quantum error correction, the ways to demonstrate that you could have thresholds, that you could have exponential suppression of the errors if you manage to have your physical error low enough. But then they were kind of like not really used anymore, except as maybe a pedagogical tool to understand about quantum error correction. But then you had the surface code, and then you had more efficient codes recently, like these LDPC codes beyond surface codes and so on. But then recently, like over the past few years, there were some new results using concatenated codes. I think originating with the work of Ayata Yamasaki and colleagues, where they showed that you could use this kind of schemes to get constant rates. So this rate that Mike was talking about, the number of logical qubits to physical qubits, you could have it constant. So this is great because it means that if you add more physical qubits to your system, you also get in the same proportion more logical qubits. So this is really, really what you want to do. And so they get a constant rate with these concatenated schemes with only a polylog time overhead, because as also Mike mentioned, you don't want to transfer your space overhead to a time overhead, and here they showed that you can do that. And so more recently, building on this, there was one paper that I find funny, surprising maybe, although maybe not surprising, that surprising in hindsight, but I find nice. It was this paper by Craig Gidney and Tiago Bergamaschi, I think. It's called Constant Rate Quantum Computer on a Line, I think. And so it's funny because they use this result and then they built a quantum computer that has constant rates, that has this polylog time overheads, and that can that can work on just a line, so like local nearest neighbor connectivity. And this can seem a bit counterintuitive or even in contradiction with some foundational results in like information theoretic results about bounds that you have on the encoding rate and the correction properties of geometrically local realization of codes, things like the Bravi, Poulin, Terral bounds. But it's not in contradiction with it, because this is something that Reddit always talks about. Like you shouldn't care only about the quantum error correcting code, but you should care about the circuits that implement it. And if you look at the global picture, taking into account the circuits and not only the code, then you can go beyond this kind of bounds. And so this result, where they have these very nice, very efficient encoding rates with not a very big time overhead, and that can fit on the line, is a kind of funny and somewhat surprising results that I liked.
Yeah, I didn't actually read that paper in detail, but is it just like a theory result, or do you think this could have like practical implications?
So it's a good question. I was wondering, I think per se, this construction on the line is not really practical, but I think in the same category of results, you can have things that could have very practical applications. And so related to that would be also from a few months ago, this paper by Dana Litinsky about what he called blocklets, that is also using this code concatenation. And so having something that is very efficient, that has very good properties, using low weight measurements. So it's not low density, but it's still low weight. And so it is very practical, this scheme. So in the end, seen in that way, I think it has very practical applications.
Great. Paul?
Okay. Is it working?
Yeah.
Yeah. Okay. Cool. Yeah. So essentially, I was thinking of taking the same paper because it really surprised me as well. The fact that it was actually possible and completely counterintuitive from what we expect on the connectivity side aspect of quantum error correcting codes. But now that it's taken, I should improvise another one. So I'll take the one from Riverlane on like the directional codes, which is also a surprising result. It's based on a local connectivity graph, so 2D grid, and trying to do to look at whether you can do non-local codes, implement non-local codes with this restricted connectivity. And essentially, they proved that this is sort of the case to some aspects. You cannot do extremely non-local, but you can do much more non-local than what the connectivity can do by using some gates that are actually native in Transman qubits. So that's kind of nice and a bit surprising to me that that works super well, because that's even better than what you would expect to be able to do with a surface code, because normally the surface code for Transman qubits has been explored. That's the standard, the default one. That's the experiment of Google, for example. But the CZ gate or the CNOT gates are not the native gates from Transman qubits. So actually, the ISWAP gate that they're using in that paper is a native gate, and it actually can do better. So that's really nice. So sorry if you took this one, but
Joan?
That's great. Thank you. You've done my homework for me, so I don't need to talk about that paper. Yeah. So that's a nice result, and it comes hand in hand with what you were talking about before. That there's been this paradigm shift now on how we design quantum error correction codes, and we no longer think about the stabilizer formalism so much anymore, and we think much more about building fault-tolerant circuits. And when you change perspective like that, there's like new doors that open, including these kind of codes that seem to have more non-local stabilizers that you would expect with local connectivity. I guess that results that have surprised me over the last year or so, there's been this reducing algorithm costs using the surface code, using different tricks, including concatenating the surface code with yoked codes, and lowering a lot the cost of preparing magic states. So magic state is this very valuable resource that you need to use to do universal quantum computation, and historically it's been the most expensive part of your quantum computer. So like 90% of your qubits you should devote to distilling these magic states that you need to consume in order to do quantum computation universally. But there was this nice paper on magic state cultivation by Kidney and collaborators recently, in which they lowered this cost tremendously. And now the cost of distilling a magic state is roughly the same cost as doing a CNOT gate, which was one of the cheap gates to do on the surface code. And just doing that, they've managed to lower the qubit count that you need to break RSA by a factor of 10. And that's impressive. So that's, I think, one thing that really surprised me is this is the fact that we can still lower algorithmic costs by orders of magnitude, doing what are really quite simple tricks in quantum error correction. And then there's been all this flurry of activity around the bivariate bicycle codes and these proposals by IBM. And this is very exciting. These are these codes that have better encoding rates than the surface code, similar thresholds, but they require this non-local connectivity. And something that people don't talk about too much is that these codes are actually very hard to decode. And if you want to use them in practice, you'll need to decode them in real time. So every microsecond, you'll have to return your correction to your quantum computer. And if you just take them at face value, they're just so much harder to decode than the surface code that it's quite a daunting problem. But there was this paper in May by the IBM group on something called Relay BP. And well, the word is not very important, but what's important is that the usual strategy that people were using to decode these codes until now was combining two different strategies from classical error correction. One is called belief propagation, and then you had to do some post-processing on it. And by playing some very clever and very non-trivial tricks, the IBM team managed to kind of do away with the second step. And that's going to be very important in order to decode these codes in real time and to actually make these things useful. And actually, we were talking to Jake Ambetta in IEEE a couple of weeks ago, and he was saying that decoding these things in real time is the #1 problem that keeps him up at night. And well, they've made good progress, but there's still kind of strides to finish this.
Thanks, Christophe.
Yeah. So yeah, maybe I can second a few points that were made along the way. So I really like the recent trend in like thinking about circuits instead of static codes, and the idea that yeah, you're going to like really look at the space-time kind of structure where the errors happen. And people have been thinking a lot more this way, and it brings a lot of things to optimize. And there are tools to think about that, like so more and more quantum error correction people start to use this ZX calculus, which is like a graphical language, which I really like. And I think it's really good. It's a really good tool, useful tool to use to think about these kind of things. And now for like a result that was kind of surprising, and also a trend that I like to see coming back, is starting to, so there's a recent renewed activity in thinking about local decoders. So that means that decoders that really could be parallelized and just need to look locally on the whole system at what's happening to decode everything. And with at Inria, there's a student who we've been working that developed an actual decoder for that, for the 1D repetition code that not only like works in theory, but also in practice is pretty good. And I found that surprising and kind of exciting that you can have these like very minimalistic decoders that do pretty well like in practice. And I think this kind of revived the idea of this whole grade of the kind of the self-correcting memory or the autonomous memory, something where you have a very well crafted system. Maybe you have to spend a little bit of energy in it, but most things are taken care of by themselves. And I really like to see this more work renewed on this area, because I find this fascinating. Like, is this possible or not? I really like this question.
Great, thanks for the very interesting, insightful thoughts, guys. So I guess I wanted to maybe switch gears now to, I think everyone here is a theorist, but I think everyone also has some expertise in thinking about QEC for hardware. So I wanted to just ask you, for your kind of hardware platform that you know best or you work on, what are the kind of like key challenges for QEC that you're kind of working on, or you think maybe more people should work on? And maybe we can go the other way this time.
So I think
maybe say a bit about the hardware platform, explain what it is as well.
Yes. So currently, so working at Alice at Bob, we look so superconducting circuits in which we don't have this like transport qubit, but we have like modes, and we do this cat qubit, which is a bosonic code. But most of the like control and kind of constraint of the platform is very similar to regular transport qubits. So I think one thing that's very that's very challenging, and I'm really impressed when I see like the progress of my experimental colleagues along this way, is like getting out of the sort of hero experiment paradigm and really getting into the robust development of this kind of systems. And I think this is one of the big challenges that will like accelerate a lot of things, like make this very robust.
Yeah, Joan.
I think you're asking about quantum powered mic, but one thing I'll say is that it's very important also the classical hardware you put around.
That I'd be very interested to hear
the
your
quantum
opinions
computer.
on that.
So so I'll just I'll think about what's familiar to me, which is the decoding problem that you need to solve in real time, megahertz type of frequencies for the fastest qubit types. This is very difficult and very non-trivial. This is the latencies that you require to the decoding in real time. It's not something that happens anywhere in the world, I think, and there's no communication system that requires responding in a microsecond time. So this is really quite the challenge. We also work with qubit manufacturers. Actually, this is a very important thing to us. We need to learn how qubits work in practice, and then kind of going now to the quantum hardware. There's obvious advantages and disadvantages of each platform. Some of them have been mentioned already this afternoon. So we talked about trapped ions and neutral atoms, which have amazing fidelities, very long coherence times, but they're also slower, like 1,000 times slower, roughly speaking, compared to superconducting qubits. So I think these qubit types, at some point, they will need to speed up in order to finish computations really in reasonable amounts of time. There's been, we heard from Yuval, from Quandela, that there's been some good progress, algorithmically speaking, but there's more to do on that front. And maybe on solid state qubits, one problem will be with that you have the yield problem, right? So these qubits, you manufacture them, and then you have them printed in whatever wafer you used. And fabrication methods, I think they're not up there yet. And there's going to be dead qubits in any chip you make, and having a better yield is maybe one of the main challenges in these platforms.
Yeah, maybe to just kind of follow up on this. So Christophe was talking about recent progress in local decoding. And do you think having local decoders will solve this like software kind of problem of classical hardware, or not? Like, what I mean, if you can find one where you have good performance, so is it much easier to implement these with like FPGAs? I imagine so, but I'm not an expert on this.
It's hard for me to comment. I know. I mean, I was in QEC and I saw this nice talk about local decoding. I would like to understand this better. I don't know for certain. In my mind, still to decode properly, you need to decode a window of D by D by D physical qubits. We've tried to break this problem into smaller bits, and every time we tried, we failed. I would love to see it working in practice. Yeah.
Thanks, Paul.
Yeah, so I was actually a former experimentalist, and I kind of really agree with Christophe's statement on the fact that getting the robustness is super important, because like most of my experiments only work for 1 day or two, and then completely die after. So getting that to work for like a really systematic way, really reliable way is really challenging. And more on the photonic side, I think one of the main challenge of getting there fault tolerantly is actually to reach the fault tolerant thresholds, because they are actually extremely difficult to reach for photonics. The main one being that each time we put an optical element, we have photon loss, and we need really to mitigate as much as possible this loss to be able to do to get to 90+% transmission for the full life of a photon, and that's actually extremely difficult. I think for the moment the record is roughly 70% transmission, so we are still a bit far, and that's the biggest challenge from an experimental side. And I think from a theoretical side, the objective is to make it as easy to reach, to increase this kind of thresholds as much as possible, so that to make experimentalist lives a bit easier.
Boris?
Yeah, so unsurprisingly, I would say the same as Paul. So yeah, I work at Quandela, and so at Quandela, our roadmap for photon quantum computing is based on using spins and photons. So we have these semiconductor quantum dots that have a spin degree of freedom that we use as a qubit, and they emit photons, and we use the photons that they emit to perform gates, spin gates. And this is basically the rough idea of the way we want to do photon quantum computing. And so it means that we need to reach some performances on the spins, on the photons. So we need to have spins that have a long coherence time. We need to have the photons that are emitted by these semiconductor quantum dots, they need to be very indistinguishable. And then the photons that are emitted by these quantum dots that are sent together to the same place, so that we can then have spin-spin gates. They need not to get lost, as Paul said. And so I think that from our point of view of the QEC team in Quandela, one important line of research is finding schemes that are as efficient as possible in correcting losses, so that give us the highest loss tolerance that we can have. So looking at different codes, looking at different concatenation schemes, looking at a lot of tricks, adaptivity to really get this threshold as high as possible. And another thing that I would like to mention is the question of time, of matching all the different times and clock cycles that you need. So you mentioned decoding time, and indeed, like we want to do things very fast, to have a high rate for our computation, but we will have a bottleneck with decoding at some point. So we want to be very, very fast, but still in a way that we can decode real time. And this has consequences on the characteristic time for all our operations, right? So we want, for instance, for us, we want to have spin that have very long coherent time, and at the same time, we want to have spin-spin operations, so like this photonic gates, to be as fast as possible, right? Because you want the ratio of this operation time to the lifetime of the qubit to be as big as possible. So you want fast photonic operations, you want long coherence time for the spin, then you want your fault-tolerant gadgets to be as efficient as possible, so that you can extract the syndrome in a very effective way without too much of a overhead. And you want all of these to be reasonable enough for it to be decoded. So it means that you have a lot of constraints, related constraints that are about the classical part, about the decoding part, about the actual quantum system, about the fault-tolerant protocols that you implement. And so making sure that all these times are matching each other, that they all make sense when you put all of them together, is something that is challenging because it involves all of these constraints at the same time.
Great. So I was thinking that it might be nice to also open it up to questions from the audience. So I'm going to ask one more question, but have a think in that time if you want to ask a question to the panelists, and then we'll open it up afterwards. But yeah, I guess my question is, all of us here have worked in academia and industry at various points. And then my question is kind of, what do you think, is there a difference at the moment between the kind of research questions you work on in academia versus industry? Is this important, or are we in an era where everyone's kind of working together? I'm just kind of interested in your thoughts on this, both at the moment and as we go forward, as hopefully we keep making progress. So maybe let's go back this way, starting with Boris.
Okay, so I think it's a very interesting question, and indeed, I think for people who've been working both in academia and in industry, it's always like interesting to think about these things. So I think there are like general differences between both, and so not specifically for quantum error correction, but that then have consequences for quantum error correction. So I think in academia, for instance, typically the way you work would be like project-based. You define a question that you find interesting, based on your past research, based on discussion with colleagues, based on discussion with people in the new group where you arrive, based on discussion at a conference, and you define a research project that is well connected to the state of the art and to the community of researchers, and you work on trying to solve this question, and then typically the end goal would be to publish a paper about it, potentially with follow-ups afterwards, but you want to resolve this question, and then you can work on projects that spans different topics, and then, yeah, I would say one of the defining things is that publishing a paper is kind of one of the end goals. And then you work in a very expert way on some topics, really like with a very, very good knowledge of a field, but to a point of specialization that requires to be very, very high. While when you work in a company, typically, I would say that you will be focused on a common goal that is, for us, quite simple: building a fault-tolerant quantum computer with the hardware that we have in Quandela. And so it requires to have more discussions, I would say, between the different teams, to have better integration of the hardware research, the theory research, building a common vocabulary, building common knowledge, to really work all together towards that goal. So I think that, for instance, for quantum error correction research, it means that we will be focused on the kind of challenges that we have to solve for this hardware, and it means that the research questions that we will be interested in are motivated by the hardware, by the constraints that we have, the type of connectivity, the way we can do the gates, the native gate sets that we have, and so on and so forth. This will really fuel the kind of research questions that we want to solve. While in academia, maybe you can have more blue sky research, for instance. But that being said, I think that the field of quantum technologies, in particular quantum computing, is maybe one where this distinction is the least relevant, because I think now there is a lot of collaboration between academia and industries. In France, for instance, we have like CIFRE PhD students who work with an academic supervisor and an industry supervisor. You have a lot of collaborations where we have academic labs and industries. So this distinction tends to be maybe less stringent than before. And another factor, I think, is the fact that you have now companies that have very big research departments, very deep pockets, and so they can afford to do very, very far-reaching research, let's say. And I think this was maybe less the case before, but if you look at companies like Google or IBM, for instance, they can afford to do research without to have at least some lines of research that are maybe very high risk, but very high reward potentially. And so it means also that this distinction between, let's say, application-oriented versus blue sky research is less accurate in quantum computing.
Paul?
Yeah, I totally agree with that. Maybe what I can add is also the fact that when you are in academia, you have also the goal of training new researchers. And that's an important one, particularly in QEC, where there is kind of a shortage of researchers. Probably a lot of people here have troubles recruiting experimented researchers with PhDs or after. So then I think there are not a lot of differences in the type of research that is done in academia and in the private sector. Probably in the sense that, for example, when you ask a question in a quantum-related topic, that could be a really pragmatic question. For example, how I create a more efficient quantum computer or whatever. The answer will probably need to go to really deep and really fundamental types of math or physics to answer this question. And usually the papers from the private sector are as foundational on really specific topics than the one in academia. They're not on the same topics, but they're kind of using the same elements and the same, for example, you mentioned ZX, stuff like that. It's kind of the same solutions that pops up whether in academia or in industry. Yeah.
Joan?
Yeah, please train more PhDs on quantum error correction. There's really a shortage of talent now. Everyone is hiring, and it's a tough market. I've been on both sides of the field, and I think we're in this very sweet moment now where industry and academia are collaborating, and we very nicely in quantum error correction, and we have these conferences where we meet and discuss. I hope this lasts as long as possible, but you can tell that some people many people remain very open in quantum error correction, but this may not be the case forever, right? So if you read papers on experimental results, a few years ago you would see photographs of the chips, and now you don't see photographs of the chips anymore. You see diagrams, right? So at some point, I expect that things are not going to be as open as they are now, but right now it's a very sweet moment of collaboration. And I agree with everything that has been said. Academia is really the place where you can really do blue sky research and explore really ambitious ideas. And as has been said, in the last few years, there's been a lot of foundational results that actually have come from industry as well. Maybe one thing to say about industry is that you're really forced to think about whether what you're doing is going to make sense in the long term, right? So we really need to build a working fault-tolerant quantum computer for all of us to have a job in a while. So this is really very important. Maybe when you're in academia, it's great if you make it work, and if you don't make it work, you move on to the next problem. And in industry, you're so forced of focusing on the problem of scalability and working with the qubit providers and so on. You really focus on the pain points of scaling up. So I guess that's I think both things are necessary to have a fertile field. But there's a different emphasis, and I think, I hope the collaboration we have right now will last for many years.
Yeah, I agree, and I think there's been big advances in the theory of quantum error correction that came from industry. So it's a really fruitful back and forth at the moment. Christophe?
Yeah, I can add also collaboration between companies. I think is at the moment really fruitful, and I hope it also lasts as long as collaboration with academia. I don't think, the general sentiment is, I think, very spot on. There's really there's a difference in focus versus curiosity, and I really think so. Both these things are really crucial to development of any science, any technology. And maybe the quantum computer object is a bit special at this moment right now, because it's such a, when you think about it, it's it's an amazing object that's so complex, and that's really a mix of still research question hidden in between layers of engineering, and that's why this collaboration is so valuable and useful, and should stay for, I think, quite a long time. I think this is really this object is fascinating.
Yeah, I agree for sure. Okay, so now we've got a little bit of time left, so I'd like to open it up to the audience. Please don't be shy. If you have a question, raise your hand. Yep.
I've got many questions, but one is, as far as I know, QEC is highly focused usually on correcting poly errors. And we see the emergence of stuff being done to correct leakage errors, erasure errors, correlated errors, and it depends on the qubit modality. What's your thoughts about this, and particularly thoughts about how would the focus change as we scale in the effort you are doing to correct all these errors all together?
Will the focus of like the solution or the yeah, I guess it depends a lot on like how well the scaling up of like logical error rate or scaling down, if you I don't know how you works, right? So this poly approximation is really like comes from a really convenient and yet powerful way of describing errors. And already people have seen that in some cases it's not enough, and I've like worked on fixing that as for simulation and everything. So yeah, I think it's really seeing it as it goes. Like there's also these like coherent errors. There have been some works in a few years back where simulation were like promising in showing that maybe at large scale you don't need to care that much, but it's something also to be verified. So it's very, I would say, like that there's no clear path with respect to like knowing now what will be needed, or if anything else will be needed.
I think the natural thing is to focus on the most damaging error that you have, and for many platforms these are Pauli-like errors, but there's going to be other platforms like photonics or maybe atoms where you can lose your qubit, and then loss might be your dominant source. Some other platforms you engineer things so that your main source of error is actually not Pauli. So there's these erasure-based qubits, and you know, if you have if that's your dominant type of error, you can actually protect against twice as many errors compared to Pauli errors. Yeah, that's my answer. I guess one other thing I want to point out is that in their foundational or milestone papers, Google, they also look at these very rare events. So usually you make some assumptions to prove that the error correction will work mathematically, and one of them is that you will have local and decorrelated noise. But one thing that you see when you make your error correction code very big is that once in a while you have these very rare events that completely destroy your performance. So these are not a pain point now because you need to be carrying about very long distances, but at some point when we are in the large scale regime, these are going to be important. So we'll see as we go. Yeah.
Any more comments?
I think everything was said roughly.
Okay, we have one more question. I think this will be the last one.
I have a question more towards education of people that are getting into the field of error correction. Something that I have found as somebody also coming from a different field now, more into error correction, is that it's a very technical field. And you mentioned, I think all of you mentioned the word tricks many times. And so papers are full of tricks that are kind of very important. And finding them is very difficult because sometimes they're hidden in appendixes or things like that. And sometimes it's very basic stuff. Yeah. So how would you train a new person into the field, especially if you know the tricks yourself? Of course you can tell them, but sometimes they have to get to learn about things that nobody in the team knows, right? And so other than reading papers thoroughly and just going through it, like do you see a better path forward?
I think maybe just a quick, like everyone is waiting for a Gottesman book. So there's some PDFs are circulating around, but once the book is really clean, it's probably a good one.
So I can definitely relate because I actually started doing quantum error correction not so long ago, and it's a very big field, very complex, and with huge literature, so it's hard to navigate. And there are things that are very surprising in the first place if you're not told, and very confusing. Like, for instance, I remember that I was very confused in the first place because sometimes, especially maybe in the older literature on quantum error correction, people call decoder basically the syndrome extraction circuit. And now when we talk about decoder, we're more having time like the decoding part of the circuit. And at first I was very confused about that, or people called cat state what everyone else calls GSZ state. So I was also very confused about why Gottsman was talking about cat state all the time, for instance. And so I think that for all these things, that's why it's so important to work with people who are experts, because, I mean, you have the impression that you can learn everything from like, or not you specifically, but sometimes we have the illusion that we can learn about things from reading papers and that we will understand the paper and move to another one and understand more. But indeed, where there are so many things that are, some things that are just kind of, yeah, you know, they're written like this, but it's not really what is meant, but everyone know that it's supposed to be this and so on. If you just read the papers, you will never get that right. And so that's why it's so important to actually get trained in a place where you have people who are experts, who've been in the field for a long time, and then who can guide you in noticing what's important, what's irrelevant, and so on. And so that's why it's very important to have good academic groups with, as Paul was saying, where the goal is to train people, because then it's just something that cannot be replaced by just training on your own reading papers, right?
Maybe an additional point is something that I discovered pretty late, but classical error correction is nice also to understand quantum error correction. Do that first a little bit.
Yeah, I think barring Gottesman's book, I don't think there is a book on quantum error correction where things are explained in a standard way. But there's tooling now that kind of make things a lot more standard. And now, thanks to the advent of Steam, this great tool by clicking the kind of people are using code. It's much easier to share code and to reproduce results from other people. And maybe if I'm allowed, I'll do a shameless plug. So at Riverlane, we've been working on educational materials for quantum error correction. And if you just go to our website, you will see advertised it in very big letters. We have some software packaging that can help you use Steam, something called Delta Kit, and it comes with a book as well. So maybe you can learn stuff from there.
Great. So I think we've run out of time, but thanks. Let's thank all the panelists for a really interesting discussion.